All right. Hi, everyone. Thanks for joining us today. So we're here today to talk about good and recommended model settings for fast execution. And for that purpose, we'll take some time today to look at the example of a Simulink and Simscape Electrical model and go through the process of analyzing the model and looking of some recommended steps you can take to make sure they execute fast. My name is Eva. I'm an application engineer at MathWorks, focusing on physical modeling, and I'm joined by Gernot today.
Yeah, my name is Gernot Schraberger. I'm also application engineer. And well, typically we have two scenarios where this content is relevant for you. One is either you want to set up a fast running model where you already know at the beginning that execution time plays a big role, or you might have a model that is running too slow and you want to accelerate it. We have here this live stream to give you an overview how to deal with this kind of problems. We will focus everything on a specific model that we have built up and tweaked a little bit, that not everything is optimal at the beginning. But important is we also have a lot of additional videos in the video series that are pre-recorded and you can find on YouTube. I can just show you here. If you go to the link down in this invitation, look for a video series link, you will come here to a page where, for example, you can see Eva here with one of the chapters here, for example, Solver Profiler. It's a video series of 15 topics, going a little bit more into detail. And you will also see here download code. If you click on here, you will get all the examples on GitHub, so that you can reproduce the scenarios and adapt it to your specific own models that you have. Well, I go now to this prepared model. You can see here a model with a PMSM, permanent magnetic synchronous machine. And the control of this machine, we have got here the synchronous motor. We've got an inverter here. A very typical setup. Then you can see here the controller section. It's a field-oriented control. We have got a PWM generator here, Park-Clark transformations here, and inverse transformations. Then a current control loop here with ID, IQ control, and then a speed control loop here as the outer loop control. So that's the scenario that we have. And typically, I would say at the beginning, you make a run and measure the time. And measuring the time is something you can automate here by using here model properties and adding here one output dot simulation metadata timing information at the stop function callback. That means every time you execute the model and you press the stop button or it runs till the very end, you will get timing information about initialization time, execution time, termination time. So all the important times of the complete model. And I think that's absolutely relevant if you want to improve the speed to really focus on these times.
So it's a bit more detail than TikTok would give you, I guess.
Yeah, I hope so. Well, now let's start this first execution. I press the play button here, or the run button. You see the model is compiled, initialized, and we're in the running.
Maybe while this is running, feel free to post your questions in the chat. We'll try to answer them as they're coming in or also at the end of the session today.
Thanks, Eva. Great idea. Well, you see it takes some seconds already to run through the model. And something you cannot see here at the moment is that I have the scopes opened. I can click here on one of the scopes and you see, well, we are indicating the signal progress here. And yeah, we'll just wait till the very end. And that's not the only scope that is opened. If you go here and here you can see there are 7 scopes opened at the same time. So why do I mention that? Because, well, I've got this experience already, but we can figure out where do we lose most time here in the model. Therefore, I would suggest to go up here to the debug section, debug tab, click performance here, Simulink profiler. And the Simulink profiler, you can click the execution button here in the profile section.
Maybe before you start executing, do we want to take a look at what the initial timing was of the model?
Good information. Well, we have here initialization time 4 seconds, execution time 44 seconds. I think that's the most critical time in most cases. So it took 44 seconds to run this model of a length of 0.2 seconds. So I would say it seems to be slow.
It's a bit much slower than real time, definitely.
Much slower than real time at the moment. And yeah, and now we go to the solver profiler and have a closer look where this loss of time is coming from. And therefore, as I mentioned, I have to click here on the profile execution, not on the normal execution, but in the profile tab execution. This will take typically longer now compared to the normal run because a lot of logging happens in the background. But it's not important to wait for the very end of the model. We can just stop it after a few moments like now. And we have a kind of relative view of the blocks, which blocks takes longer compared to the other ones. And of course, not the absolute length is important, but you have to have a certain understanding of the content of your model. Certain expectations where you say, well, this block I expect to take longer compared to another one. And then you can see, well, does this expectation fit to those things you see here in the report? And what you see here is the total model has execution time for that short moment I executed now of 8.6 seconds. And we have always a self time and the complete time of single blocks or subsystems. And for example, what does it mean here? 8.6 seconds is the complete execution time of the model, and 2.7 seconds is the execution time only, it's a self time only on that hierarchy level. And if we sum up all the other blocks, we will fill up that light blue bar here.
So this would allow you to kind of compare which parts take longer and which takes not that much time.
So it's you can find that here on the hierarchical level. That means on the top level, you have here scopes that take relatively long. Then the next block here is solver configuration, which is a block for the Simscape part. It's much slower compared to the scope. And that indication here as well, scope is critical. It takes a long time. Are there alternatives? That's the big question here now.
So it's probably a good idea to get rid of the scopes first and then see how it runs without them.
Exactly. And that's what we're gonna do here. I just close these windows here. I go to all the scope blocks now. And I think there are 7 in here. I can comment them out. So they're not active any longer. And then I can say, well, I want to see some results, of course. Yeah, otherwise simulation wouldn't make sense. I can use logging, signal logging, by just selecting the lines and going here to log selected signal, as you can see. And this data will then be recorded and shown in the simulation data inspector. You can see this icon here. At the moment, it's not indicated in yellow color because nothing has been recorded so far, but we will see with all the iterations we run through that all the data is recorded there, and we can even compare them later on. Yeah, and to see if the results are the same, because that's the second important thing. It's not only about speed, it's also about fitting results. And every modification of the model, of course, typically will change the behavior slightly. And it's the question, is it acceptable or not acceptable any longer? So I would say important feature here, use the data inspector. You have got the chance to compare the results. And what we'll do here now is we just go through the single steps and we have a look to the initial simulation and to the very last simulation and compare the results there just to see if things still fit together.
So in reality, we'll probably do this step by step, but just for the sake of time, we'll do it at the very beginning and at the very end.
And we're a little bit limited with the monitor here. So let's repeat the simulation. I don't do it from the Simulink profile any longer. I just run it here. We had, I think, 44 seconds.
Yeah, so overall it was 49 seconds, I guess. And 44
but 44 the execution, the runtime. And of course, if a simulation takes longer than 0.2 seconds, which is the stop time at the moment, only the execution time will expand and not the initialization time. So we just have to wait till the end here. And we'll get immediately a link where we can see the outputs of the model. And one of the output is the execution time. So we click on here. And we see, instead of 44 seconds, we are down at 27 seconds.
All right, so we already gained like 16 or 17 seconds just by removing the scopes.
Only the scopes. So that's already nice. Yeah, we can have a look to the data inspector already, short look, to see what we can see there. And I wonder why nothing is recorded here at the moment.
Seems to be correctly locked. Something maybe.
Presentation effect.
Let's give it another try.
Now, yeah, we have to repeat it once again. I don't know what went wrong here now. But now data inspector changed to yellow color. And that means something is recorded.
Data should be available.
They should be available. And that's then our first run without the scope. So we can remember with the scopes, we had 44 seconds. Now it was, I think, 27 seconds. But, well, scopes don't change the values, the signal values, so it's uncritical.
And there it is now.
Here it is now, yeah. And we can already select the channels here because we will need them later on anyway. So we can say, well, RPM is one of the values we're interested in, Newton meters. And down here we have, for example, the currents of the three phases. Let's click on them. Okay, and for the moment, I think we won't go back here step by step because it's a little bit complicated to demonstrate. We have at the very end, we have a look if the results are the same for the first and the last simulation. Yeah.
Right. Maybe let's continue by having a look what's going on in the model, what kind of solver settings have been chosen for this model. So on the very high level, on the very top level, we can see in the bottom right here, ODE 14X is the global or the Simulink solver that has been chosen, which is a fixed step solver. And to get a little bit more insight about what's going on and maybe what kind of sample times we have in the system, we can go to a additional visualization option by just going to debug and going to the information overlays and selecting sample time colors, meaning so this will trigger a model update. I won't run the model, just an update. And then the different sample times present in the model. Just zoom out here so we can see everything side by side. So we can see different sample times present in the model. So at the moment, it looks a little bit, well, a little bit messy, maybe not as it was intended to be by whoever created that model or what was the purpose of the model. So on the right in the timing legend, we can see, okay, there's something sampled at 2 microseconds. That's, as we can see, the output of the PWM generator. Then there's 500 microseconds going on as well. It's highlighted in green. So it looks as if this was intended for the control loop, but it also seems we can see some black signal pointing to a continuous time signal. So probably it was intended to have the controller running in fixed step, but it didn't really happen, at least not completely. So there's still things to fix right there.
Well, what I see very often, Eva, is that people use the continuous controller blocks, for example, or filter blocks, because they're used more to the Laplace domain. It's easier for them to parameterize those blocks, and they forget about the timing, if it's a discrete time system or if it's a continuous time system. So that's maybe one of the problems here. But I think it's also important to mention what is the goal of the simulation,
right,
because it's very important. If we want to optimize a system, of course, it plays a big role. What effects do we still want to see in the simulation and the results, or what effects we are not interested in? For example, if you are interested in power losses during the switching, of course, you need a very detailed model. On the other side, if you're interested in a model for control design or for harmonics analysis, you need different fidelity levels. And I think that's something we have to have this clear information, what level of fidelity is needed. What are you expecting as the goal of the simulation?
So in this case, the purpose of this example model we're showing here today is to perform a harmonic study. We'll also talk a little bit later, at least, about different fidelity modeling options that are available in Simscape. But this will be the purpose for today's presentation or for today's stream. And what we also can see, if we zoom out in this model again, is that the bottom right, so the sort of Simscape part of the system, is also somewhat highlighted in red. So it's intended to run fixed step. And what we can also, it's called, the blocks are somewhat highlighted in red, so pointing to the update rate. So for Simscape, there are a few cases where you would run the Simscape model at a fixed step rate. For example, if your plan intend to do a hill simulation and need to generate code for that, or for some models where you have a lot of switching going on, it might make more sense also to run in fixed rate. But oftentimes, when we're doing the same things we're doing today, so doing more desktop simulation, you would usually go for a variable step solver for the Simscape model, and you'll still be able to run the controller in fixed step and have it side by side running with a variable step model in Simscape.
That's an interesting aspect that some people might not know, but you can mix, as you mentioned, model, the plant model, so the physical model in variable step is a possibility, and the controller very often is, of course, in time discrete or fixed step
especially notation. To generate code at some point. And also, even if your final goal is to run the plant model in fixed step, you probably, when developing the model, would still run it variable step to have some kind of a golden reference when you're trying to change it. So if you we'll just go through that example right here. If you were to run the model in fixed step, so the Simscape part of the model in fixed step as well, what we usually recommend, so right now we can see the global solver is ODE14X. And if we go into the solver configuration block that's attached to the Simscape network, we can see that the local solver option is turned off. So this is typically something you would enable. So the Simscape network itself would have its own fixed step solver. We can see we already have the update rate is already put in here, so we don't have to do it. Yeah. So this would be what's recommended for if you were to run the entire thing in fixed step. So maybe let's run it again to see how it compares.
Yeah. So I click on run here.
So the last one was 27 seconds.
27 seconds.
Runtime.
Let's see if it's faster.
Correctly.
I think it does a good job.
Yeah, we'll see what the result says, but it looks a bit faster.
So let's have a look to the diagnosis.
So
10 seconds.
Around 10 seconds. So that's less than 50%.
Yeah, we started with 44 seconds. Now we are at 10 seconds already, just with a few modifications.
As I said, for the purpose of this simulation, we intend to run desktop simulations also for the Simscape model. So it's probably wise to have a variable step solver globally and then make sure that the controller loop is updated at a fixed rate. So
I think there's also something I want to come back here. It's the continuous.
Yeah.
The continuous timing here. What do you think about that?
So out of experience, I would say that the user probably thought it would run in fixed step because the solver was set to fixed step, and it's all taken care of. But what usually happens is in a lot of Simulink blocks, you have this sample rate setting where it says inherit or -1 or something similar, and it just inherits from incoming signals. So you can see here there's a step function at the very beginning that's creating the velocity reference, and it looks as if it's inheriting from that setting and is putting out a continuous time signal. So you can see there, Gernot already opened the block interface for the PI. So you can see here the sample time is set to 0, so it's continuous sample time. So we probably want to make sure by explicitly setting the sample rate of all of these blocks to make sure at what rate they are running.
So we should use the green rate here now because it's the control system, and there is
to run it.
TSC is the variable that I can put in here. It's 500 microseconds. Yeah, it does not change here. We still have the continuous PI controllers. That's also something I would correct to say, let's go really to time discrete mode and not mix things with discrete sample time, but continuous description. You need a solver there, which does not really make sense. So we can go in here and
set it to all to the same settings with the same sample rate.
We can just click here on discrete time instead of continuous time and use the sample rate TSC, which is the 500 microseconds also here. So we have 2 of the controllers, a third controller here. Okay.
Right. So
let's make the update
this again and see what the changes brought.
Yeah, it's more consequent now. We have all in green here now for the controller.
So the controller is in green now, meaning 500 microseconds. PWM is still putting out the gate signals
and the rest is in red. So I think that's interesting. Does that change anything in timing as well? It's at least cleaner, I would say.
I would say the same thing,
But let's check it.
So we're still running the Simscape model at fixed step.
We had
and the global solver is still at 6 step. We had 10 seconds.
10 seconds was the time before. So just discretizing the blocks. Where are we now? Oh, 6.4. That's not.
No, not so little actually.
It's about 40%. That's a lot, So you see, small changes can change your life here quite a lot. Yeah.
So maybe as we're still working with sort of desktop simulation, let's go back to set the global solver to be variable step and also remove the local solver from the Simscape model.
Yeah, I think the main idea here is for the variable step that if we run, the controller is still in fixed step, time discrete, but the PWM, you have this high accuracy there of 2 microseconds compared to the 500 microseconds of the updating cycle of the duty cycle. So most times nothing changes. So the idea is if we go for a variable step, maybe it does not have to go for every single step. It just has to find the locations where the PWM switches. And that means we can jump over certain times when nothing changes in the model. That's the main idea here. So
and this is something that the variable step solver can do. So it has the capacity to take larger time steps where the model allows it, but also to make sure the time step is small enough to solve dynamics of the system. Okay, so Gernot just changed the variable step solver. So he chooses a ODE 23T here. So this is, out of experience, typically a good solver for models containing Simscape or Simscape Electrical blocks in our case. There are a couple of them, like 15S or DAE SSC, which is one that is specifically for Simscape networks that usually work well for stiff systems, which Simscape models often represent.
Yeah, typically. So let's use the 23T here.
And also, like before you closed it, just below the solver selection, you can see like the tolerance values. So this is something that appears as soon as you have a variable step solver because it can adjust the step size to satisfy the set tolerance, which then in after setting that, make sure the solver solves to a specific tolerance you set. And also, maybe I should note here, there's a check mark that is not a box that is not enabled in this case, the auto scale absolute tolerance just below the absolute tolerance value. This is something that's typically turned on for Simulink models if you start with a blank Simulink model, but it's something that is not recommended for Simscape models. So it's turned off here as well.
Okay. I think more information about that will be found in one of the videos, which is only about solver settings. So for every single task we perform here, there's much more material in the video series, and you can reproduce those things in the models we put on onto GitHub. So we've chosen our variable step solver.
Oh, yeah, and maybe make sure to remove the local solver, otherwise it won't apply to the Simscape network of the model. Yeah.
So, yeah, because we are now in variable mode, and we rerun the model.
Okay. Let's see. So the changes, as you know, compared to the last one, is changing from back to variable step to variable step solver. Let's see what this brings.
So what we can see in the timing colors is we have continuous in here because of the variable step solver. I think that's automatically done like that, but we have still 2 microseconds and the 500 microseconds. I would have expected a little bit different here, but we'll see later why that's the case. First, have a look to the time. We got better a little bit. So from 6.5 seconds about that down to 5 seconds when we use the variable step solver. And now, well, there is another setting. I want to start with the lower hanging fruits, I would say, and not to go into complicated modifications already now. One of the low hanging fruits in speeding up a model is surely here the simulation mode. So we are running here in the normal mode at the moment, but we have also got other simulation modes. And one is, for example, the accelerator mode.
It sounds good. Sounds like a good.
Let's click on that. It's telling us that the profiler, Simulink profiler, is a little bit limited, but nevertheless it would work. We will not test it here now, but it is working more or less, delivering the same information. And yeah, let's give it a run. So 5 seconds was the last value. Accelerator mode needs more time for the initialization because it compiles the model. That means the compile time is extra time, you will see. But nevertheless, execution time should be shorter, especially if you have larger Simulink sections in the model, which is the case here, I think, because we have all the controller PWM generators based on Simulink. Simulink is typically running much faster if you use the accelerator mode. So let's have a look here. Yeah, we came down from 5 seconds to 3.83 seconds. Got a little bit better. Initialization time got up. So that is getting worse because of this additional compilation of the model into C code and into binary. That's extra time. That means accelerator mode makes sense if you have models that are not too big maybe and that are running relatively long.
Longer profiles maybe or something. Yeah.
So in most cases it makes sense, but you have to test that. So this initialization time, of course, that's not so nice. What can we do against that? There's one important mode here called fast restart. So if I select fast restart, for the first time I run the model, it behaves exactly the same as before. So we can do that. We will see about the same execution time as before. But then if it's once has finished, it will be frozen in a pre-initialized state. That means all this checking of the model, did something change, and those things will not occur any longer. Nevertheless, you can change parameters.
So it would be good for something like if you do a parametric sweep and just need to change some parameters for that, but the model structure stays the same.
So what would be possible? You could, for example, change here in the PI controller. You could change the setting here. I won't do it here now because then we get other results. But that would be possible here in this mode. As long as you don't change the structure. If the structure changes, of course, things won't fit together. And the idea behind is that you can have so-called tunable parameters. And tunable parameters are even found in the C code which has been generated here as variables. And of course, they can be reassigned with new values without having to recompile the model. If you change structures, of course, the code is a different one. That's something which it will not be allowed here. That means you have to leave then the fast restart mode and change the structure, save the model again. And then, of course, you need this initialization time once again. But now let's stay in the fast restart mode. And
should we have a look at the diagnostics viewer first to see what the timing was of the fast restart run?
Yeah, it was 4.59 seconds in initialization and 3.9 for the execution. Now let's do the second run here.
Already noticeable that it didn't really initialize.
It's 0.5 seconds. It's much faster now. Execution time is about the same because nothing changed there. It's just about the initialization time. But of course, that's an important feature. And there's even one point I have not mentioned here now. It's the thing that even in the physical modeling section, that means in Simscape, you can change parameters. Here, they are not called tunable parameters. They are called runtime parameters. So if you look, for example, to the inertia, well, it's grayed out at the moment because we cannot change the structure. So take out the fast restart, go in here again. Now we can modify something. You see the J is a variable. And there is a setting here, configurability, compile time. That means at the moment, it's compiled in the code. It's not the J in the code as a variable, but it's the fixed value of 0.2. If we want to have this changeable with the fast restart mode, we have to change that to runtime parameter.
So I could start it ahead of a simulation without recompiling the model.
And a good idea is not to do that everywhere in the model. If you have a large model and you set all the parameters to runtime parameters, that might slow down your model execution as well. It just makes sense to do it in those locations where you really want to change parameters in your parameter sweep or during an optimization, for example. Okay. I think the speed up we have seen, that was just a little bit background information about that. And well, I think these were the low-hanging fruits. Now we continue with this 2 microsecond sample time, where I expected before this should be continuous because we changed from fixed step solver to variable step solver. And we expected, well, to have not a fixed 2 microsecond sample time, which means we still are calling the model much too often. So where's it coming from? It's coming from the PWM block here. It's the only red line here. Also that one, but that is because of the go to from connection. So it's related to the gate pulses here in the PWM generator. So let's double click on the PWM generator. That's one block from Simscape Electrical. We see the PWM generator here itself, plus an on delay block. On delay, what does it mean? It's a block where, if you look in here, it's called on-off delay. You can delay the switching in case of on switching or off switching. And this block has the idea to prevent short circuits. That means the high and the low side of the IGBTs or MOSFETs are not switched at the same time, but there's a short time delay in between. So that's something I have seen very often in customer models. And the other thing is the PWM generator itself. It's also delivering the first time the red signal. So if we look in here, well, we get the configuration mask, but we can look under the mask by right-clicking here, mask, look under mask, and we can analyze what can be found here. The PWM, how does it work typically? You have a time value that is very often generated either by a function like here, or it's also using here an integrator to generate these ramps, for example, a triangle waveform, which is compared then with a fixed value coming from the switching times that are applied here. So switching on and switching off times. You see here, that's a time discrete integrator. We want it to be continuous now on the physical side, not on the controller side as before, but on the physical side. That's causing this problem. So question is, are there better ways to do a PWM generator? And I would say yes. There's even a chapter in the detailed videos, but just for the short presentation here, you can see I have several variants here set up. And there's a second variant here where I generate the PWM in a different manner. And let's also have a look to this log here. So was it grayed out?
I think if you once you Control E,
Control T.
So we do a model update again, so it applies the.
Yeah, it's easier to see than. Yeah. What you see here is we are coming in here with the red signal, and be careful now. We have lost one discrete sample time. So red is the first discrete sample time, but now it's 500 microseconds. So that's the rate from the controller now, which makes sense. We make update of duty cycles here in any way, or of the voltages here. And what you see out on the output side, we have just continuous sample times. So what did change here now? Let's go in here. The first section of the PWM generator is the calculation of the switching times. That means if you get a duty cycle, you already know at the beginning when to switch off and switch on the PWM, depending on low and on the high side. So we get two switching times. The first one is on and the second one is off. Then, yeah, there's some tricky part in here. Just for compatibility reasons, I wanted to have this PWM compatible with the setup before. We had a discrete timing before, and even in realistic implementations, you have a PWM circuit, a digital circuit, where you have to program a register, for example, for a specific switch on and switch off time. So that means it's not completely variable concerning the timing. And that's the reason why I bring this time that has been calculated here, coming as an input from the duty cycle, I bring that to a fixed raster. And I do that with seal and floor rounding functions. Then I'm in a fixed raster, and the raster, once again, is a 2 microsecond raster from before, but it's not a fixed sample time any longer. That's a tricky thing here. And then I come in with the time here. I have the duty cycle on and off times. And this one is a block from the Simulink library. Yeah, it's a PWM block from this from the Simulink library. And that is realized or implemented in a different way. It's not going through the block and looking for duty cycles, but it's really pre-calculating the duty cycle and says, oh, now it's the switching time, and it's just calling the variable step solver at the switching time. I think you can see that also relatively clear if you have to analyze that in the solver profile. And maybe I have to go one step back. I go back to the former situations where we had the default 3-phase PWM generator. And if you say, well, it might be hard to find it, maybe Eva, you can show how you can use solver profiler here to do that.
Yeah. So yeah, as Gernot said, we have recorded a bunch of videos on the different tools available. So we have a more detailed video on the solver profile as well, but I'll open up here as well just to be able to analyze this model. So let's wait a second for it to open up. There it is. Get it over here. So the solver profiler is, you would typically use it when you work with variable step solvers because it's good to analyze what's going on and what is maybe making the solver slow. So if you're trying to answer questions like, what is maybe constraining my time step? Why is my solver stalling at certain points? So this is where the solver profiler is a good tool to just see what's going on or analyze what's going on. So we'll just run the model from here. I'll first make sure that additional data is collected, and I'll just run the model from here. So once this has run the model, it will display me some sort of general statistics on the model, but also give me more detail about where the time step was small and maybe what blocks or states mostly contributed to the time step maybe being small, maybe even too small for what I would expect out of the model. So let's see that this is finishing up collecting data. So,
yeah, you can even stop that. I think it's not about runtime. We can.
Yeah, you're right, but we're almost there.
Yeah,
so let's finish this up. Or let it finish up. Right. So once this has run, or as Gernot said, you can also stop it ahead of time if that's already enough information for you. So on the left, we see some general statistics. So something like what's my simulation time, what solver has been chosen, but also what's the largest step time taken, what's the model runtime compared to its simulation time, what's the average step size, and what kind of events have happened. So something like a zero crossing events. These are the types of events that might make a model perform poorly. And on the right-hand side here, I can see, so this is a plot of, maybe let me make this a bit larger so we can see more of the plot. So this is a plot of the time step taken versus the simulation time. So when it dips down, we can see where the simulation time step taken is smaller, but we can also, if, for example, choose to highlight different types of events that contribute to that time step being small. And something we can see sort of on the bottom here, there are different tabs. So one is just give some general suggestions or just some diagnostics the solver profiler has identified. But I can also see like what's contributing to the time step being small. And what we typically see are things like solver exceptions. So there I can see like where the solver failed to meet my tolerance requirements. So earlier we talked about with the variable step solver comes the option to set tolerance values. So I can see where the solver failed to meet those and needed to put extra steps. So this is something, for example, you can see in the error control, like what variables contributed mainly to the error control. But I can also see like what type of solver resets happened. So events that made the solver reset. And one of the contributors is typically something like zero crossings. This is something we can also see in more detail right here. We can see like what type of blocks contributed to those types of events.
And I think what's clearly to see here, if we zoom up or if we look to the plot, you see the time step of 2 microseconds for the most of the time. I think this can be interpreted in the original model that we have still this fixed time step in there from the PWM. Sometimes we have zero crossings. Yeah, but now maybe go back and change the block as we have just indicated before as a comparison. So we once again go to this fast Simulink variant that I've shown before, and we rerun the model. And of course, it's important to do that from the solver profile again.
There again.
So I click here and run again.
So this is now running the model where you intend the PWM to generate continuous time signals to be allowed to take larger time steps.
I would not expect to have this fixed maximum value here.
Yeah, exactly. Because that would allow it to take larger steps.
Take larger steps. That was the main idea from before. And we can stop it here now. Maybe after some time. So it's processing data. That's strange.
Okay, so it's still there. Maybe let's see what's going on in the
wrong in the model. Let's update that. Yeah, it seems not to have changed that.
It seems to have run the same model as before. Maybe let's change it again and rerun it. Yeah, so now it's the right one.
Now let's rerun. And as Eva mentioned, well, we have to focus on the zero crossings now. We have seen them, but the first thing was, well, there's still this limitation. We have to get rid of the limitations, but then let's have a closer look at the zero crossings.
And by the way, feel free to post some questions if you have any. We'll have some time later, after the presentation part or after the demonstration part.
So let's have a look once again. Yeah, now this limitation has gone. So we are more flexible here, but if we zoom in here, we still have a lot of zero crossings. So that's something I would not have expected. We are still periodically lowering the step time to very small times because of zero crossing. We can see that here. And
yeah, so Gernot just clicked on the zero crossing tab, and like every line indicates, in this case, a certain block that's triggering that zero crossing, so we can exactly see which block is at fault here by generating so many zero crossing events.
We can click on here and highlight the block, for example. So this is this comparison. Comparison is generating a zero crossing because it's enabled here. So we have to go back here and see where is this coming from. And it's coming from the on delay block. So it's the block I explained before. It's to prevent the short circuit. So that means we have here continuous gate signals. So that worked fine, but we still have this high amount of zero crossing. And that's clear because, I mean, even if we calculate the switching times more efficiently now, it still uses zero crossing to find, to add some additional time. And that's, of course, not very effective. So, of course, we are prepared to that. We have another variant here. And this other variant, I want to show you here. If we look in here, we have taken out that on delay block, and we have brought the on delay block into the logic here. And that means where we had before, we had 6 PWM generators with the logical connection here to generate the correct switching on and off times. Now it's 12. We have doubled them. And we take care about this dead time. You see this here in the block that is indicated. So the idea is really to pre-calculate the switching times now separately for high and the low side to prevent zero crossings. So let's execute that.
Maybe
and
from the profile again, or
or let's do a time measurement and have a look at the profiler.
Maybe accelerator mode first, so we compare normal mode, or
no, we have chosen the accelerator mode before. Let's continue here, and I just have forgotten which time we had been before.
So last
2
time
seconds,
we
2-3 seconds, or 3 seconds, I think it was.
More like between 3 and 4.
Yeah. So we're at 2.4 seconds now. Yeah. Okay, initialization time is still high because we don't use the fast reset, but we are permanently modifying the model, so that wouldn't make too much sense at the moment. Yeah, and we can also repeat that in the solver profiler just to see what changed here. If we have a less number of zero crossings, we don't have to go through the complete simulation, but just a short time. A few percent, yeah, it's fast. You see it down here. It's much faster here now. So there are still some things, of course, going on, but the zero crossings are here.
Like the major source of the zero crossings have been removed, and there's still some in there coming from the Simscape Electrical, from the inverter blocks. I guess.
The zero crossings, it's yellow. I think that's important to see. Up there, that these are not zero crossings we had before, but we see in the list it's
less in there. Also, the intention of that, it's not to get it down to zero, because you have some dynamics in the model, so there will be some events happening, but the intention of that is kind of to give you some pointers to where things could not be behaving as you intended it to behave.
And that can be the diode, for example, in the IGBT. the anti-parallel diode, which can cause the zero crossing. It's part of the functionality.
Yeah, part of the physics.
Yeah. Okay. Let's give it a last run. I want to see if something changed, even if we've done that. But sometimes the second run is a little bit faster. And you see, wow, it's really fast now, 2.3 seconds. I think that's really good. That's a good time. Yeah. Well, I think that was the PWM now. What else can we do? We can have a look here to the plant model. And we have inverter here. Let's look in here. We have single components used here for the inverter. It's IGBTs. It could be MOSFETs as well. If you look in here, you see it's an ideal switching converter or ideal switching IGBT. That means we have a piecewise linear model, which is surely much faster compared to a nonlinear model. And I think the goal we had before was to increase the speed for a model that is used for harmonic analysis. So I think that's absolutely fine. Just to give you an impression how the time will change if you go here for another option of the detailed model, for example. And you've seen 2 seconds of run. Now, if we repeat that, and I think as far as I remember, we don't have the chance to wait until the very end. It's relatively slow compared to before. But now that's a simulation where we could, you see, well, 1-2%, it's extremely slow. So we stopped it here. But this is a simulation. If you want to analyze the switching losses for a detailed model, then you will need this mode, but you would not run such a model for a long time. It's just to analyze certain scenarios, and you take the data and apply them on a table, for example, for a faster simulation if you're interested in switching losses.
And as Gernot just showed nicely, there are typically different types of model fidelity options available. Again, it also, of course, depends on the type of question you want to answer with your model.
Yeah. There's even a third option here, which is, if you look under the mask here, which is using a compact block, converter block from the library. If you do some analysis here, you will figure out that it's running fast. Again, it's a comparable time comparable with that one from before, with the ideal switching, because it's also using ideal switching. Yes.
So basically the same setup.
It's more or less the same setup, yeah. And I expect to have also about 2.3 seconds, well, 2.02 seconds. But there's some statistical variance also of this time. So I think that's quite fine here. Yeah, I think for main things we have shown here now, there's only one different thing I want to mention here, and which you can also find in the video series. It's if you want to run parameter sweeps, intensive parameter sweeps with a lot of combinations or test cases or optimizations, where you have to run a single model again and again with different parameterization. If that's the case, there is another option which is called parallel computing. So it's an option where you can use a script to set up the problem. And I can just give you a short insight. I haven't prepared it here now for this model, but just to give you an idea, this is actually, these are the files you will find in the file exchange. And here in the section parallel computing, you will find the script here for parallel simulation setup for normal or accelerator mode. So if I open that file, you will find always a description here so that you can work with that, apply that to your own models. Fast restart and simulation modes also play a role here. And you see the exactly setup of such a problem for parallel computing. You need so-called simulation objects to organize all the parameterization data at once. You have to choose here, for example, also organize the parameters here in for loops, so prepare all the setup, as you can see here. And then there's also an option, for example, to use the fast restart together with accelerator mode. And that typically will increase the speed of a simulation dramatically, because typically you will have more than a single core in your machine. In the practice, of course, also the memory plays an important role, because every instance of MATLAB Simulink requires a certain amount of memory. So there might be also memory limitations, but if you have a very powerful machine, or if you want to run that in the cloud, for example, or on a computer cluster, there are, I would say, no real limitations here.
This is also something you can use, for example, if your model run is part of an optimization problem.
Yeah, right.
You could also use the parallel computing option.
So that's how these files are organized. It's always a live script where you have to start. There's some explanation here, an overview, the motivation, or the use cases that you will find here, like parameter Swiss, Monte Carlo analysis, and so on. And then you run through the example and apply this setup to your own examples if you have to really to speed up your specific model in that case. Well, I would say we are nearly at the end. There's one important thing still missing. We have to look to the data inspector. Yeah,
we only looked at the first one, but not the other ones. But maybe let's compare with the last one.
So we see here we have the archive. We have all these runs. We have done 16 runs here now. We have one setup. I think it was of the run 2.
What was the first one? The first one is still displayed.
The first one is displayed, yeah. Now let's click here additionally on the 16th to see, are the results still the same? That's an important thing. You have to do that. Otherwise, yeah, you might simulate things wrong. You see small modifications, yeah. We changed the model. Yeah, it's not 100% the same. That's also important. You have to check just if it's fitting to your requirements.
Yeah, it's to be expected to be changed some things in the model, so it is to be expected that some behavior might be different. It's about, as Gernot said, answering the question, is it still what you need for what you're trying to do with the model?
Yeah. Yeah, and down here, let me see here, the A. Yeah, there are small deviations, and it's really depending on every single step how far they are or not, but in most cases people say that's acceptable. And yeah, we started, I think, with 44 seconds for simulation execution time.
Around 2
seconds.
That's pretty good, I would say.
That's pretty good, yeah.
All right.
Well,
yeah, so as Gernot said, we have more videos with more detail on different analysis tools, also different modeling options. Those are all linked just below this video, also with the corresponding files. I think if you all have some more questions, again, continue to post them in chat. We'll see what kind of questions have come in and see if we can answer them. Right. So Brookflix is asking, apparently cannot see the same type of solver settings we are seeing, or the types of solvers. I might not be understanding the question 100% correctly, but maybe it seems like, so you should, if you have Simulink, you should see all the solvers we had available. So maybe make sure to change between variable and fixed step. So depending if you choose variable or fixed step, there are different types of solvers available. So maybe it was just due to that you couldn't see the same solvers.
Just to show that again. Yeah. So here we have variable step solvers, fixed step solvers, and then we have the selection of the individual solver algorithms. Yeah, the solver video and also some other videos will go into more detail about that. Yeah. And the fixed step solver, we also have a certain selection here. I think for Simscape, I would always use the local solver for fixed step. It's always faster and more robust. Only if you go for variable step solver, look for the stiff solvers here.
Yeah. The only thing that is a bit of an exception is the DAE SSC. That one you only have available when you have Simscape.
Right. Yeah. Well,
all right.
What's the next question?
Okay, that seems to be it. Just a comment. Somebody just starting with the tools. All right, that's good. All right.
Yeah, I think that's it for today. Check out in YouTube. We are still working on other chapters.
Yeah. It will continue to grow.
Yeah, it will continuously grow. And you can start with the 15 videos. I think that's something to do. Well, we wish you a nice day and hope to hear from you.
Exactly.
And well, see you.
Yeah. Thanks for joining today. See you.
Bye.